Namaskar. I am Dayan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the homogeneous equations of order n with linear equations with constant coefficient. Constant coefficient. The equation we can consider the equation L of y is equal to y raised to n plus a1 y raised to n minus 1 plus a2 y raised to n minus 2 plus dot dot plus a n y is equal to 0, where a1 a2 a3 dot dot an are constant. This equation is a homogeneous equation of order n. Now theorem on it: homogeneous equation of order n. Let R1, R2, R3 dot dot Rn be the distinct roots of characteristic polynomial P of R is equal to R raised to n plus a1 r raised to n minus 1 plus a2 r raised to n minus 2 plus dot dot plus an. Suppose R1 has multiplicity m1 mi m1 plus m2 plus dot dot plus mn is equal to n. Then n functions e raised to r1x, x into e raised to r1x, x raised to m1 minus 1 e raised to r1x, e raised to r2x, x into e raised to r2x, dot dot x raised to m2 minus 1 e raised to r2x, plus dot 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 are solutions of L of y is equal to y raised to n plus a1 y raised to n minus 1 plus a2 y raised to n minus 2 plus dot dot plus an y is equal to 0. Now see your proof. Suppose Ri is the roots of P of R of multiplicity mr. Then P of R is equal to R minus Ri raised to mi Q of R, where Q is a polynomial of degree n minus mi. Now differentiating P of R, mi minus 1 times, we get P dash of R is equal to R minus Ri raised to mi Q dash of R plus mi into R minus Ri raised to mi minus 1 Q of R is equal to R minus Ri raised to mi minus 1 Q dash of R into R minus R1 plus mi Q of R. P double dash of R is equal to R minus R1 raised to m1 Q double dash of R plus 2m1 R minus R1 raised to m1 minus 1 Q dash of R plus m1 into m1 minus 1 R minus R1 raised to mi minus 2 Q of R is equal to R minus Ri raised to mi minus 2 into R minus Ri square Q double dash of R plus 2mi R minus Ri Q dash of R plus mi into mi minus 1 Q of R is equal to R minus Ri raised to mi minus 2 polynomial of order n minus mi, and so on. P raised to mi minus 1 of R is equal to R minus Ri raised to mi minus mi minus 1 polynomial of order n minus mi is equal to R minus Ri polynomial of order n minus mi Therefore, P of R is equal to P dash of Ri is equal to P double dash of Ri is equal to dash dash is equal to P raised to Mi minus 1 of Ri is equal to 0. Let e raised to Rx be a solution of L of y is equal to 0. We see that L of e raised to Rx is equal to P of R e raised to Rx, where P of R is equal to R raised to n plus A1 R raised to n minus 1 plus A2 R raised to n minus 2 plus dot 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 plus An. Therefore, L of e raised to R1x is equal to P of R1 e raised to R1x is equal to 0. Thus, e raised to R1x is a solution of L of y is equal to 0. If we differentiate L of e raised to Rx is equal to P of R e raised to Rs k times with respect to R, we obtain dou by dou r k times L of e raised to Rx is equal to L of dou by dou r k times e raised to Rx is equal to L of x raised to k e raised to Rx is equal to p raised to k of r plus k p raised to k minus 1 Rx plus k into k minus 1 divided by 2 factorial p raised to k minus 2 r x square plus dot dot plus p of r x raised to k e raised to Rx. Thus, for r is equal to Ri and k is equal to 0, 1, 2, 3 dot 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 mi minus 1, we get L of x raised to k e raised to Rix is equal to 0. Therefore, x raised to k e raised to Rix k is equal to 0 to r. Solutions of L of y is equal to 0. This is true for every characteristic roots Ri with multiplicity mi, that is x raised to k e raised to Rix, k is equal to 0, 1, 2, 3 dot dot mi minus 1, I is equal to 1, 2, 3 dot dot s are solutions of L of y is equal to 0, and the result follows. Next theorem, the n solutions of L of y is equal to 0 given in theorem are linearly independent on any interval I. We prove that a function given in theorem 1 satisfy the conditions given in definitions. Suppose we have n constants Cij, I is equal to 1, 2, 3 dot dot dot, yes, j is equal to 0, 1, 2 dot dot mi minus 1, such that C10 e raised to Rx R1x plus C11 x into e raised to R1x plus dot dot dot, and this way pi of Rx is equal to Ci0 plus Ci1x plus Ci2x square plus dot 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 plus Ci mi minus 1 x raised to mi minus 1. Then pi of x e raised to Rix is plus p2 of x e raised to r2x plus p3 of x e raised to r3x plus dot 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 plus ps of x e raised to rsx is equal to 0. Assuming that not all constants Cij are 0, then there will be at least one of the polynomial pi which is not identically 0 on I. Suppose pi of x is not identically 0 on dividing equation by e raised to r1x, we get pi of x p1 of x plus p2 of x e raised to r2 minus r1x plus p3 of x e raised to r3 minus r1x plus dot 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 plus ps of x e raised to rs minus r1x is equal to 0. Upon differentiating, and we get rs of x e raised to rsx is equal to 0, and this is gives the solutions of theorem. Right.